Okay, so this is for the individual mastery checkpoint 3. So we have to suppose a thin rod, the cross-section area of 1 centimeter squared, has a mass distributed according to the density function, P of x equals 5x cubed sine x squared grams per centimeter cubed, where the x and distance seen for left in the rod. If the rod is 3 centimeters long, give an expression involving one or more definite integrals of the exact mass of the rod, include units. So first, I accidentally computed the center mass of the rod, but actually, the mass of the rod is just the integral from a to b, then p of x times d of x, and it'll be in grams or whatever unit we're in. So I did the mass from 0 to 3, because that's how long the rod is, from 0 to 3. So the a value is 3, the a value is 0, the b value is 3. 5x cubed sine x squared x dx, and that will be in grams after you evaluate that integral. So going to 2, we consider the region ky is 1/3 y, and h of y is negative y squared minus 2/3 y plus 6. So we have this equation right here, that equation right there, and that equation right there. So we have to sketch and label a representative slice for the computing area of the region bounded by k of y and h of y. So I did that. So originally I thought it would be like this, but then I rethought and I'm like, okay, it has to be like this instead, because we are evaluating in respect to y. So the representative slice, its height is changed in y, and its width or length would be this value right here, 1/3 y minus y squared minus 2/3 y plus 6 times the change in y, because that's how you find a area of a rectangle, which is base times height. So, and I graphed this equation, the two equations here, and that's not the slice. The longer slice is, and that's the change in y. That is also not correct. So the change in y is the actual slice width, and that's actual slice length. So then we have to integrate in respect to -3 to 2, and because that is the because that's where the y value is here. It's -3, and the y value up here is 2. So then after that, we put that in the integral form from -3 to 2. And that's 1/3 y minus y squared minus, because those are two negatives, it will be 1/3 y plus y squared minus 2/3 y plus 6, and then that will be integrated in respect to dy. So going into problem 3. Find an expression involving one or more definite integrals, which is the arc length of h of x equals negative x squared minus 2/3 x plus 6 from x equals 1 to x equals 5. So we take the arc length formula, which is the integral from a to b times the square root of 1 plus f prime of x squared dx. And then we have the arc length equals and the integrals from 1 to 5, because that's what it says right here, x equals 1, x equals 5. So we're integrating from the length 1 to 5 times the square root, or we're just evaluating, at this 1 plus, and this is the derivative of our equation right here, -6x plus 2 over 3 squared dx. And if we solve that, we would get the arc length, because that's the value if you solve this. And so, hold on a second. So, sorry, I had a call coming through. So, now we're going on to 4, in which is consider the finite region S bounded by 4x minus 1 and x to the third minus 1. So we have n of x equals 4x minus 1 and m of x equals x to the third minus 1. So I graphed it here first without the reflection, and the points are 0, 1, and the points of intersection are 0, 1, and 2, and 7. So now I decided to flip it because we have to flip it according to y equals -1. So -1 is right here. So I flipped it across the y-axis and then I drew the small slice right here, or the inner slice right here. This is the outer slice. So I drew the representative slice out. So the inner slice is -1 minus 4x minus 1, because we have to take into account this difference in 1 right here, because that's the point that we are reflecting around, because we're rotating around this axis. So our r of x, or our little r of x, is -1 minus 4x minus 1. And then our width is the change in x. And then, because that's what we are integrating to. And then the big value, the big R of x, is -1 minus x to the third minus 1. So then after that, we have to state the volume of the representative slice from B. So the V slice is pi times -1 minus x to the third minus 1 squared, because of the pi r squared formula. Then we have to minus that, -1 minus 4x minus 1 squared times the change in x, because that's what we are integrating in respect to. So then after that, we have to find an expression involving one or more definite integrals whose value is the volume of the solid revolution generated by revolving S around y equals -1. So we integrate in respect to 0 to 2, because that's the change in the x values from here to here, 0 to 2. And after that, we do pi times -1 minus x to the third minus y squared minus -1 minus 4x minus 1 squared dx, because we are integrating in respect to x. So now, going to number 5, we have to consider a rectangular dam that's 81 feet wide and 314 feet tall. So that's what the water rises to within 100 feet of the top of the dam. So I drew my little picture here, and because it's 81 feet, 314 feet, and then that's the difference in height of the water. So we have 0 to 40.5, that's our little point here. This is 314 here. And then our point at this end of it would be 314 and 40.5. So we take these 2 points, 314, 40.5, and 0, and 40.5, and we set them into a y equals equation. So we do 40.5 minus 314 over 40.5 minus 0. And this is because we have to cut this in half for the representative slice. So 81 divided by 2 is 40.5. So we do, then this would be our slope right here, -273.5 over 40.5 plus 40.5, because that's, again, half of 81. So then after we... So our representative slice for computing the area at a given depth would be the change in x times this equation right here, y equals -273.5 over 40.5x plus 40.5. So, sorry, it will be 2 times that. So 2 times this, 2 times -273.5 over 40.5x plus 40.5x times the change in x feet squared. That is the equation of the expression that gives the area of representative slice from B. And include units, it will be feet squared, or the change in x feet squared. So then we have to set up expression that gives the pressure at any point on the slice from B. So we just take the pressure of water, or the average density of water, times x minus 100, because we don't have any water from 214 to 314 feet. And after that, we have to compute the force the water exerts on the slice. So we just have the F slice equals P slice times area slice, because the force equals pressure times area. So we have the F slice is 62.4 times x minus 100 times 2 times -273.5 over 40.5x plus 40.5 times the change in x feet squared. So that would be the equation or expression that gives the force the water exerts on the slice from B. So then we have to have an integral. So we have to evaluate this integral from 100 to 31.4. Oh, sorry, 100 to 314 is from A to B because the depth of it is not completely full. So we have 62.4 times x minus 100 times 2 times negative 273.5 over 40.5x plus 40.5, just times d of x because we're integrating in respect to x on f. So going to extra credit, I just grasped some two equations. My h of y is 1/4 y, my g of y is negative 0.02 y squared, and I rotate around, that should be x equals negative 8. I did that. My graph kind of looked like this. It is not very neat, but this would be the 2 points that it is integrating around, or the slice, and so it kind of looks pumpkin shaped. So I have my 2 points, negative 27.204, my 2 y points, and I have 14.704 here. So I'm integrating from negative 27.204 to 14.704 times pi times negative 8 minus 1/4 y minus 8 squared minus negative 8 minus 0.02 y squared times dy. So then after that, we get our equation of 29,137 millimeters cubed, and I thought that was the most reasonable answer for that. I tried it to be neat, but so yeah, that is it for the pumpkin and the end of my individual mastery checkpoint 3. Thank you for watching.